Rafael Ortiz Imedio, entitled Performance of Low Carbon Fuels in Integral Combustion Engines, supervised by Professor Immaculada Ortiz and Dr. Alfredo Ortiz. The thesis has been developed in the framework of the PhD program in Chemical Engineering, Energy and Processes in the Department of Chemical and Biomolecular Engineering of the University of Cantabria. And before starting with the defense, I would like to introduce you the members of the examination panel. So, as this is an hybrid defense, the international member of the committee is present with us through Teams. I want to give a warm welcome to Dr. Georgios Kosmalakis. Georgios, could you switch on your camera for a moment?
Yes.
Okay, thank you.
Tell me if you can see.
Okay. So, Georgios Kosmalakis is a senior researcher engineer in the National Center for Scientific Research, Demokritos, in Greece, and he's also research associate in the National Technical University of Athens and in the Agricultural University of Athens. Also, I'm glad to introduce you to the secretary of the committee, Dr. Salvador Ochoa, who works as research and development engineer, and he is the head of combustion technology in Siemens Energy, which is located in Vitoria, Spain. Finally, I would like to introduce myself. I am Eugenio Bringas, and I am associate professor in the Chemical and Biomolecular Engineering Department of this university, and I will act as president of the examination panel. Also, I would like to inform that the thesis fulfills with the requirements to be awarded with the international mention at the University of Cantabria. The candidate performed a 3-month research stage supervised by Dr. Martin Robinius in the Forschungszentrum Jülich in Germany. The thesis has been positively informed by 2 doctors from foreign research institutions, Professor Said Hosseini from the Tarbiat Modales University in Iran, and Dr. Carmen Rangel from the National Laboratory of Energy and Geology in Portugal. So also the document of the thesis is totally written in English, and also the presentation will be completely in English as well. So according to the doctoral regulation of the University of Cantabria, the defense will consist of 2 parts. First, the candidate will explain the work carried out, the methodology, contents, and conclusions of the research, with particular attention to its original contribution, and then, after the presentation, the panel members will make as many comments or questions that they consider appropriate. So, Rafael, the floor is yours.
Thank you very much. Buenos días. Welcome to the dissertation of my PhD thesis entitled Performance of Low Carbon Fuels in Internal Combustion Engines, supervised by Professor Immaculada Ortiz and Dr. Alfredo Ortiz. This thesis has been conducted in the Chemical Engineering, Energy and Processes PhD program in Santander at the University of Cantabria within the Chemical and Biomolecular Engineering Department in the Advanced Separation Processes group. This thesis has been financially supported by the European Regional Development Fund with the Pensudo and Atlantic projects, and by the University of Cantabria with the Concepción Arenal Postgraduate Research Grant. Furthermore, the work of this thesis has been developed within the Atlantic project, focused on the hydrogen deployment in the Atlantic area from its generation, storage, and its application in the maritime sector. To obtain the international doctorate mention, a research stay of 3 months was conducted at the Institute of Energy and Climate Research in Forschungszentrum Jülich in Germany, under the supervision of Dr. Martin Robinius. Additionally, it has been evaluated externally by Professor Said Hosseini and Dr. Carmen Rangel, and we are pleased to have Dr. Kosmalakis as international member of this thesis committee. The work of this thesis has been published in 4 articles in index journals, being 10 of them as main author. Furthermore, it has been disseminated in different international conferences. Here we can see the main outline of this dissertation, and we'll start with the scope. It was estimated that the global energy consumption in 2019 was around 584 exajoules, being 1/3 from oil, 27% from natural gas, 24% from coal, and some minor percentages from nuclear and renewable energies. However, this energy consumption was unevenly distributed. we can see that oil and natural gas are the main pillars in almost all the regions with the higher shares. In contrast, coal is mainly consumed in Asia Pacific, as can be seen in the huge black bar. Nuclear is mainly consumed in Europe, electricity in Brazil, and renewables in Europe, America, and Asia Pacific. Furthermore, a direct relationship between energy consumption and CO2 emission is observed. Regarding the fossil fuel reserves, oil is mainly located in the Middle East and Venezuela, natural gas in the Middle East and in the Commonwealth of Independent States, which include Russia, and coal in Asia Pacific and North America. Paying more attention to the CO2 emissions, nearly 34 gigatons were emitted in 2020, being the 30% from electricity and heating, 25% from transport, 21% from industry, and almost 9% from buildings. Regarding transport, shipping moves between the 80 and 90% of the world trade by volume, being the 80% of this ship traffic in the Northern Hemisphere. This shipping transport accounted almost the 3% of the global CO2 emissions in 2018, and being the 70% of these emissions within 400 kilometers of the coastlines, and can be seen in the images of the ship tracks. Additionally, particulate matter emissions cause around 60,000 premature deaths by year, so it is an important environmental and health issue that should be addressed. To mitigate the climate change, the Conference of the Parties agreed in Paris in 2015 to limit the global temperature increase to 1.5 Celsius degrees above pre-industrial levels, and last year in Glasgow to reduce the global CO2 by 45% in 2030 and net zero in 2050, with deep reductions of other greenhouse gas emissions. And in order to reduce the fossil fuel dependence, the renewable energy generation has increased in the last decades, mainly based in electricity, the 60%, but accelerating fast the solar and wind energies. The renewable energies are mainly located in Asia Pacific, Europe, and North America and South America. However, some of the renewable energies suffer from intermittencies and fluctuations, which could be balanced with employment of an energy vector. In this thesis, hydrogen is proposed a very good energy vector because it can be employed in many economical sectors. Hydrogen can be generated with electricity from renewable energy sources from the grid or from industrial byproduct or biomass. It can be transported through pipelines, ships, and trucks via gaseous or liquid form. It can be stored in salt caverns or tanks, and it can be used in many different applications and sectors, such as the injection in the gas grid, industry, power, buildings, and transport. Many countries are realizing of this hydrogen versatility, and they have included it in their roadmaps, such as Japan, USA, Germany, UK, Spain, Australia, or some other organizations. Furthermore, many important projects are being deployed in different sectors, including hydrogen, like the North Hydrogen in the Netherlands, including offshore electrolyzers and salt cavern technologies, the blending of 20% of the hydrogen into the regular gas grid in the UK, the building of hydrogen green steel plant in Sweden. In Spain, for example, the promotion of a PERTE project for hydrogen and renewables with an investment of 16 billion euros. Moreover, the HYDEA project in Spain, combining solar and electrolyzers, is the largest giga-scale project for renewable hydrogen, and at a smaller scale, the Bahia Hydrogen project here in Santander. Regarding transport, the first fuel cell passenger train has been in operation since 2018 in Germany, and in Scotland, the first ferry with a dual-fuel internal combustion engine fueled with hydrogen is under study. So, within all the scope of the future energy transition, which includes the energy generation, the agriculture, industry, buildings, and mobility, hydrogen will play a key role, enabling a further penetration of renewable energies while balancing and decarbonizing the energy system. Conventionally, hydrogen has been generated with fossil fuels emitting a lot of pollutants, which is called green hydrogen. However, a lot of efforts is under development to capture the CO2, but it's called blue hydrogen, or the cleanest alternative is the green hydrogen, combining water, electrolyzers, and renewable energies. However, to build a suitable infrastructure, energy system models are required to optimize the hydrogen supply chains, from its generation, conversion, storage, and distribution, and different applications. They will be fulfilled in the chapter 2 of this thesis. Additionally, there are industrial waste streams with high hydrogen percent, like cocoa and gas, which its high energy content could be harnessed following the principle of the circular economy with a mature technology easily adaptable to gases, like internal combustion engines. Two main types can be distinguished: gas turbines and reciprocating internal combustion engines. This thesis will be focused on the second type, the reciprocating, which have played an important role since their invention, powering vehicles and generating electricity at different scales, from some watts, kilowatts, and thousands of kilowatts for ships and stationary engines. Two main types have been used usually: the spark ignition engine, fueled with gasoline, which are easy to adapt for burning gaseous fuels, and the second type, the compression ignition engine, usually fueled with diesel, require a diesel pilot injection for burning gaseous fuel. So this thesis will be focused on the first type, the spark ignition. And here we can see the main parts: the piston, the cylinders, the valve, the crankshaft, etc. However, someone here can think, but how does an internal combustion engine work? So in the most common configuration, in a 4-stroke cycle, one cycle means 4 strokes of movement of the top, the piston, from the top the center to the bottom the center, and vice versa. This means 2 revolutions of the crankshaft and 720 angle degrees of rotation. In the first stroke, the air or refuse mixture is introduced into the cylinder through the intake valve. Then, in the second stroke, this mixture is compressed by the piston inside the cylinder. Then, some crank angle degrees before the top the center, our spark is ignited. It's called spark advance. This gives place to the combustion, which will generate the useful power that will be transmitted through the crankshaft through the connecting rod. And finally, in the fourth stroke, the combustion gases are exhausted through the exhaust valve. Another way to represent the fourth stroke is with the valve timing diagram, which includes the intake valve opening and closure event during the intake stroke, the compression, the expansion, and the exhaust valve opening and closure events during the exhaust stroke. Another important graph is the indicator or pressure volume diagram, which represents the work carried out by the engine during the cycle. And two main areas can be distinguished: the blue one, which indicates a positive work, the expansion work, generated with the combustion of the fuel, and the orange, which is the pump work, which is negative. Try to change the way. Conventionally, internal combustion engines pushing forward. Conventionally, internal combustion engines have been filled with gasoline or diesel, which proceeds from fossil fuels, which are very pollutant. However, low carbon fuels could also be employed with some previous modifications of the internal combustion engines, such as the spark, the injector, sensor, coolings, etc. For instance, hydrogen provides a zero hydrocarbon emissions with a high laminar flame speed, high thermal efficiency, and wide flammability limits. However, it produces high thermal dioxide emissions due to the high combustion temperature, it has higher normal tendency, and low volumetric efficiency. On the other side, methane provides a high power performance with lower normal tendency and high volumetric efficiency. However, it emits hydrocarbons, it has a low laminar flame speed, low thermal efficiency, and narrow flammability limits. An alternative to combine the individual advantages would be the employment of mixtures, such as coke oven gas, which is an industrial waste stream mainly based on hydrogen and methane, and some minor percentages of carbon monoxide, nitrogen, and CO2. And how is coke oven gas produced? It proceeds from coke, which is a reducing agent for hot metal production, which is mainly manufactured in a steel process in coke oven batteries through cold pyrolysis. As products, solid coke, coke oven gas, and liquids are obtained. The second product, coke oven gas, is produced in enormous volumes annually, around 300 trillion cubic meters per year. However, they require to be purified with the removal of dust, tar, naphthalene, oil, sulfur compounds, and the cracking of ammonia before being employed in other. This clean coke oven gas can be used to obtain hydrogen, methane, methanol to produce steel or iron, or it can be combusted to generate power and heat. This has been reviewed in an article in the Industrial Engineering Chemical Research in the special issue, The Hydrogen Economy. Despite the high number of applications, coke oven gas is sometimes directly flared off due to safety reasons when there is low energy demand. However, this could be harnessed through internal combustion engines, producing electrical energy for the manufacturing plant while controlling the pollutant emissions. This rich hydrogen-methane mixture has intermediate physicochemical properties between hydrogen and methane in terms of lower heating value, density, flammability range, and laminar flame speed. These three gases will be analyzed with an internal combustion engine with experiments and a computational fluid dynamic simulation later in this thesis. So, with all of this scope, the two main objectives of this thesis are, first, the assessment of a futuristic European energy system in 2050 based on the coupling between renewable energies and hydrogen energy vector, satisfying the European demands and the maritime sector in the Atlantic area. And second, the evaluation of the technical and energy performance of an internal combustion engine filled with low carbon fuels recovered from industrial waste gases. It will be focused on coke oven gas, hydrogen, and methane, and this work will be carried out through experiments and a computational fluid dynamics model. Once the main scope of this thesis has been exposed, let's discuss the main work carried out and the results achieved in this thesis.